Hello, I'm Dr. James Wotton of IBM Quantum. This is another lecture on quantum computation based on the Qiskit textbook. Today we are moving on to the algorithms chapter. And in the algorithms chapter we start off by looking at some very simple proof of principle algorithms which show that quantum computers can solve problems with radically different resource requirements than classical computers. They solve problems that no one really wants to be solved, but nevertheless they make for good proofs of principle. But for that we first need to think about what we mean by the resource requirements of a computation and how we are going to quantify that. So for this, let us begin by doing the same as we did in the first lecture, which is adding some stuff. And we're going to use the classic algorithm where we write one number on top of the other and go down the columns doing some additions. So we start with 4 plus 1, a nice simple addition of two single-digit numbers, giving us a number, in this case, 5. And then 2 plus 5, 7, 7 plus 6, 13. Then we have to carry the 1, which means in the next column we're going to do 3 plus 8, which gives us 11. And then 11 plus 1, which gives us 12. So then we take that and carry the 1. And then we do 1 plus 9, which is 10. 10 plus 1 is 11. And we get our answer. So how much did we need to do to solve this problem? Well, it depends what we count as our unit of computational effort. If you were a primary school child doing this, then things like the single-digit additions are probably your unit of effort. In the best case, you just need to treat every column independently. Each will have a pair of digits that needs to be added, and you'll get something as a result. So for an n-digit number, the minimum you're going to have to do is n of these operations. But some of the columns are more complicated. When we had the result from 7 plus 6, which was 13, we had to do 3 plus 8, and then we had to add that to 1. So there we had a case where we see if we constantly have to carry, then we're going to need to do 2n different additions. And in fact, those weren't single-digit additions, but one had 2 digits in. So it was all a bit more complicated, but nevertheless, I think it's quite easy to see that the number of additions you would have to do scales linearly with n. But what if we were instead to do this in binary? So we had some different number, nb, of bits. Well, the number of bits you need to represent a number also scales linearly with the number of digits. So if the computational effort is linear with the number of digits, and the computational effort will also be linear with the number of bits, then this is all just saying that yes, our amount of computational effort is linear by going from digits to bits and thinking of adding in terms of bits instead of adding in terms of digits. We've just basically changed our unit. So it's like using kilograms instead of pounds or whatever. We've just changed the unit, but what is fundamentally being measured is the same, so any linear relationship will be preserved. But also we could think of the computational effort as being the number of gates we need to apply when writing this as a program. But again, that will also scale linearly. For each of these additions we need some collection of gates. So each addition requires that many gates, and then the fact that the number of operations scales linearly means the number of gates will scale linearly. If we think in terms of the number of transistors we need to implement those gates, again, each gate needs sort of a finite number of transistors, so everything is linear. So it's all dependent on which units that you choose, but the scaling of the relationship is preserved. So when we're talking about the amount of computational complexity required to solve a problem, we usually just talk about the scaling and don't really worry about the units. So there's a lot swept under the rug when we talk about complexity. For this we use some notation known as big O notation. And in big O notation we say that some function f of, I think I'll use n, is in the set of functions O of g of n if the following relation is satisfied: if the magnitude, so we'll get rid of complexities of whether things are positive or negative by putting some magnitudes here, if the magnitude is less than or equal to the magnitude of g of n multiplied by some constant, so constant over all n, and that just gets round all of these unit conversions. And maybe things are weird near zero, so to get rid of any of that, we just say that this has to hold true for some finite cutoff value of n. So as long as we have n above some finite value, then if we take g of n and multiply it by some finite value, then we have something that upper bounds f of n. So this just sets a bound on what the scalings can be. Now I should point out that even though really we should have something like this as the symbol, typically we abuse notation a bit and say that f of n is equal to O of g of n in these cases. So that is just something to get used to. So yeah, the computational complexity of addition we can then say is linear, which just means that we say that it's O of n, where n is the number of digits or bits. Doesn't really matter which, because all it changes is the value that we would have to put for the constant in this condition, and we don't actually care about that value. For multiplication, we can say that the complexity of multiplication is O of n squared for n digit numbers, and the algorithm that you may have learned in school is not upper bounded by this, but this is actually how much computational effort you need. It's quadratic. But there have been a lot of algorithms that have been found that are, let's call it n to the 1 plus epsilon for some epsilon between 1 and 0. So these have lowered the upper bound. Nevertheless, it's still true that the multiplication algorithm is O of n squared because it's still an upper bound. It's just not a very tight one. But we can find also algorithms with tighter upper bounds that can be expressed in this form. And I think it's still an open question whether epsilon can be reduced to 0. But also, if you look into some of these multiplication algorithms, you find some of what is hidden under the carpet of this kind of notation. Because sometimes it could be that an O of n squared algorithm is actually better and less resource intensive for a specific instance than some O of n to the 1 plus epsilon, even though the scaling is better in the latter case. If you look at the actual numbers for how much computational effort you need for a given instance, so for a given pair of numbers of a certain length, you may find that for, like 100-digit numbers or whatever, it's better to use a less asymptotically efficient method than a more asymptotically efficient method. And this is something we do see in multiplication. In calculators or in programming languages, the algorithm we use to do multiplication is not the most efficient that we know, because the most efficient we know actually only has its benefits kick in for ludicrously high numbers. This is something that we have to keep in mind in quantum computing, because we may find that the computational effort of using a quantum computer is less than using a classical computer. But at what point does the fact that quantum computers are kind of hard to build mean that this overweighs the fact that we can build classical computers and we can make bits and transistors really easily? So a complexity advantage doesn't necessarily mean that you're going to instantly leap for the more efficient algorithm, but it's a very important thing to take into account. So a couple of notes. If we have an algorithm which with the length of our input, which is often thought of as a number of digits, if the algorithm scales something like O log of n, then that's a pretty awesome algorithm. O log of n, not so bad. But once you start getting to O of n squared, then that's the point where real life programmers who have to run things are going to start to wonder whether it might not be that you can do it a bit more efficiently than that. But if we then go to the extreme of things like O of e to the O n, so where the amount of computational effort you need goes up exponentially with the digits, then that is pretty horrible. So things like this we often call inefficient, and we often think that they're just basically not worth doing. Now, in some cases, you can solve inefficient problems in a decent amount of time. So for a given problem, you have to look at what specific resources it takes to do that. But when we're doing studies from a more abstract level, then exponential scalings like this are pretty horrible. And when studying things from an abstract level, we often call things that are polynomial with n efficient, which means that they are O of n to the p, let's say, for some finite p. However, if that p is 462, then well, you might as well be exponential because that's a horrible power. And I just arbitrarily chosen 462 as a big number there. Yeah, so these are some of the issues surrounding complexity theory and it's, I think, just about enough, except that one important one to know is O1. So O1 means constant. So here we just have a 1 in there rather than something that actually scales. And so in the condition that we use to define this big O notation, it just means that if our f of n is O1, then it means that it is bounded by a constant. So there should be a 1 in there. And as bounded by a constant, it means that it converges to some value. So we can say, for example, that the number of logic gates needed to implement an AND gate is O1 because it's just some constant number. And it depends on how you actually do it as to how many you need. But whatever approach you take to representing an AND gate in terms of gates, I'm talking quantum gates here, of course, because in classical Boolean logic gates, an AND gate is just an AND gate. But if you're compiling your AND gate down to quantum gates, then the number of quantum gates you need to get that AND gate is O1. It's some number. Depends how you do it as to what that number is, but it's just some number. And so we say that it's O1. Okay, so that is one of the prerequisites for today's lecture. And the next one is to think about how applying Hadamards to bit strings works, because there's going to be a lot of applying Hadamards to bit strings in this lecture. So let's take a whole bunch of zeros, so 0 to the n, and we are going to apply a whole bunch of Hadamards to that. And what do we get as a result? So let's take our whole bunch of Hadamards. And well, we can think of what happens when we apply a Hadamard to a single zero, and that is that we get this superposition of 0 and 1. So if we do that many, many times for all of these n, then we are going to get another big superposition, and we can write that as a superposition over all x of x, all normalized by dividing by 1 over the square root of 2 to the n, where here the x represent bit strings expressed in ket form. So these are all n-bit strings. So as a single bit becomes a superposition, so does multiple quantum bits. When you apply Hadamards, they become a superposition over all of the bit strings. Now it comes a bit more interesting when we apply it not to the zero state, but to some general bit string. Let's call it S. So for this, we can note that when we apply h to the 1 state, then we get 1 over the square root of 2, 0, minus 1. So let's just take this as being a single bit version of what's going on in the multi-bit case. So let's say we apply h to one of the digits of S. Let's call it Sj. So this is either a 0 or a 1. And we get out 1 over the square root of 2 times the sum of the corresponding digits of x. Well, basically sum over 0 and 1. But to keep it general, I'm going to say that these are summing over the digits, the jth digits of this bigger bit string, x. And there's a possibility for there to be a phase out here of -1. And when does that phase crop up? Well, it only crops up in one case, which is when you are applying the Hadamard to a 1 and you are looking at the 1 part of the resulting superposition. So we can put up here Sj xj. So it's only when Sj and Xj are both 1 that we get the phase of -1. Otherwise we get a phase of +1. And so this is satisfied by this particular form of the equation, because in any other case, then that product will evaluate to a 0, and -1 to the 0 is 1. So in this larger case, we can say that this is, again, 1 over 2 to the n over 2. And then the sum over all x, and then -1 to the power of, well, something, but let's write that in there in a minute. We're going to call this s dot x, where s dot x is simply defined, and I'll put it up here, s dot x is defined as the sum over all of the digits times these Sj xj's. And you can also put a mod 2 in there, although the -1 is going to enforce the mod 2. The fact that you're raising a power, you're raising this as a power to a -1 means that the mod 2 is taken into account already. But basically, yeah, that's what happens when you Hadamard a general bit string. Let's begin with the Deutsch-Jozsa algorithm. So the Deutsch-Jozsa algorithm is defined for some function f of x, where the x are n bit strings for some n. And this function f of x will give us a 0 or a 1 for each value of x. Now we've been given it with the promise that it's either constant or balanced, and constant means that f of x is going to give the same bit value for all values of x, and that's nice and easy to write down. The balanced condition is not so nice and easy to write down, but it basically means that for half of the possible inputs it's going to be a 0, and for the other half it's going to be a 1. And we have been asked to determine whether it is constant or balanced. So that is the computation we need to perform. Our input is this function, and we need to determine whether or not this function is constant or balanced. So classically, how can we do this? Well, we can start by evaluating it on some random input, and that doesn't tell us very much. So we can evaluate it on a second input, and if those two outcomes are different, we know that it's not constant. So already we've found out that it's balanced. But if they're the same, then it's still ambiguous. We could have just happened upon two inputs that are give the same output, or it could be constant. So we check it again and again and again and again. In order to be certain whether or not it's constant or balanced, the number of inquiries we have to do, the number of queries we have to perform on this function is half the number of possible inputs. So the number of possible inputs for an n-bit, if we're using n-bit strings, is 2 to the n. So it has to be half of that, which is 2 to the n minus 1. And that is because in the worst case, we could just be hitting all of the inputs that give one particular output until we get to the halfway point when it's forced to give us the other output, because at that point we run out of values that give that particular output. So the number of queries we need in the worst case, or indeed in every case if we want to get absolute certainty of whether this is constant or balanced, the number of queries we need increases exponentially with the number of bits, which is quite bad. It's not really what we would prefer in terms of a computational complexity. So now let's think about what we can do quantumly. Well, quantumly, the algorithm is to take the 0 state for n qubits and then apply a Hadamard on n qubits, creating the big superposition that we saw before, and then applying the phase oracle for this function. What that is going to give us is it's going to give us a big normalization condition. And then we're going to get the sum over all x. So again, summing over now all of the possible input bit strings that you can have for this function. And the phase is going to be determined by the phase oracle, because from just applying the Hadamard to the 0 state, we don't get any phases, but by putting in the phase oracle here, we do get some phases. And explicitly for a phase oracle, the phases we get are -1 to the f of x. So, what does that mean? Well, in the case that f of x gives the same value for all values of x, then what is this but a global phase? So in the case that this is balanced, then basically we find that u f h over all of the qubits on the state that is 0 on all of the qubits is essentially equivalent, because it's just a global phase, to h over all of the qubits. However, in the case that it is not balanced, we can think about what would happen if we were to apply a terminal Hadamard on this. Well, actually, let's do that already. For the balanced case, let's see what happens if we complete our algorithm by doing a bunch of Hadamards on all of the qubits. So that's a bunch of Hadamards and then what we had before, which is a Hadamard on all of the qubits and 0 on all of the qubits. And since we know that this part that does not have the Hadamard, this part here, since we know that's equivalent to just a Hadamard on all of the qubits, then we know that this Hadamard is basically just going to cancel that out. And so this is going to be equivalent to 0 on all of the qubits. So in the balanced case, what we did here is we took a bunch of qubits in the state 0, we applied a Hadamard to them, we applied this phase oracle, which did nothing but introduce a global phase we did another bunch of Hadamards in order to undo the first bunch of Hadamards, and then of course we got back to our initial state, which was all zeros. However, let's move on to another slide in order to look at what happens in the other case if our phase oracle is applied to a Hadamard on all of the qubits for initial zeros. In this case, then again, of course, we have this sum over all of the inputs. Oh, and I missed out the normalization condition. With a -1 phase for each f of x and each x. Now let's apply another Hadamard onto this, and what that means is that we are going to have to transform these states. So for each of these, instead of x, it has to be replaced with the corresponding superposition that we get. So now we're going to need another variable, let's call it y, and let's put another y in there, and this is going to be -1 to the x dot y. So this is x with all of the Hadamards on, so this is what we're replacing the x with. So let's call that x tilde. So the action of the Hadamard that we have over here is to turn each of these x's into x tildes, where I'm just using that to express another superposition of now these basis states y, and then we have these phases characterized by this x dot y. But the only thing we need to really note here is that there is a term for every bit string. Oh, and of course I missed out the normalization condition. There is a term for every bit string, and those bit strings have phases which depend on what their own particular bit string is, and also what x they are representing. But the one bit string that never has any phase is the one that represents the all zero state. So we can think of this as being a big superposition of the all zero state and a bunch of other bit strings with various weird phases. And it's actually just the all zero state that we need to think about in thinking about this algorithm, because once we go back to the original equation, then we can think about, well, each of these x tildes is going to have a term which is all zeros, and the phases on all of these all zero states, because they have no phase coming from the x tilde, their phases are just given by the phases coming from the phase oracle. And we know that half of the outputs for the phase oracle are 0 and half of them are 1. So we know that half of these phases are +1 and half of them are -1. And so this big sum, when applied just to the all zero states, is going to have lots of terms which are 1 and lots of terms which are -1, which perfectly balance each other out. And so the only thing that we need to really take away from this is that the probability of getting the all zero state as the output is going to be 0, because of this condition on the balanced states that half of them are 0 and half of them are 1, and because of the interference effects that we are getting when we have a Hadamard and then a phase oracle and then a Hadamard. It means that the probability of getting the all zero state is destructively interfered away. So we have then two extremes. In the balanced case, the probability of getting the all zero state is 1. We're definitely going to get the all zero state. In the constant case, the probability of getting the all zero state is 1. In the balanced case, the probability of getting the all zero state is 0. So if we apply this algorithm, which is to first do the all zero state, then apply Hadamards on all qubits, then apply the phase oracle, and then apply Hadamards on all qubits again, and then we measure, then if we get the all zero state, we know that it was a constant function, If we get anything else, we know that it was a balanced function. And so just in one query to the algorithm, one implementation of the one query to the oracle, one query to the function, one implementation of the unitary that implements that function, we have determined exactly whether it was balanced or constant. So that has replaced a classical algorithm with exponential scaling with a quantum algorithm that is O1. And it did this by creating a superposition of all possible inputs, running the function on all possible inputs at the same time in some way. But it's not as if the quantum computer is just then being massively parallel, because we can only extract a limited amount of information from a quantum computer. So what it instead does is interferes all of these outputs together in order to give us some little useful nugget of information, which is whether or not the function globally can be characterized as one that is constant or balanced. Now let's look at the Bernstein-Vazirani algorithm, where we are again given some function f of x, which we are promised has some properties. In this case, it is one of these products of bit strings as we defined earlier, but this time we have to explicitly add in the mod 2, because again this is only going to give us a 0 or a 1 as an output. So just remembering what this notation means, it's the sum over all of the bits in the string sj multiplied by the corresponding bits in the string x, and then we take the mod 2. Yes, so in this problem we are given presumably a compiled form of this function, and we are asked to look at its behavior and from that deduce the string s, which is this constant which defines the function. So how do we do that? Well, classically we could do this bit by determining the bit s0 by taking the x for which x0 is 1 and all of the other values of x are 0. So the 0, 0, blah, 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 0, 0, 1 as our x. Because in this case, the only time that one of these is going to be a 1 is the one for x0, and so the output just comes out as the corresponding s0. So similarly, f of a whole bunch of zeros and then a 1 at x1 and then a 0 here is going to give us s1, and if we move that single one step along, then we get s2 and so on and so forth. So we have to do n queries for each of the bit strings with a single 1 and everything else is 0, and then we can deduce the value of this hidden bit string. Okay, so far so good. N is not so bad. Can a quantum computer beat that? Well, of course it can. Otherwise we wouldn't be talking about it. So what happens if you were to apply the phase oracle for this function to, again, a Hadamard on all qubits applied to the state which is a 0 on all qubits? Well, if we forget about the phase oracle for a moment, move that out of the way, of course the Hadamard on its own will produce something which needs to be normalized. And then we get a sum over all of x and then the corresponding x. And there are no phases here because we're applying to the all 0 state. But what if we were to then put in this phase oracle? Then this phase oracle does what phase oracles do, which is do -1 to the f of x. But because -1 to the f of x is defined in the way it is defined, what we have here is exactly what you would get if you applied Hadamards on all qubits to the state, which is just a bunch of qubits prepared in the bit string S. So if we were then to finally apply a Hadamard on all qubits, after having applied the phase oracle, after having applied the Hadamard on all qubits to the initial state of 0, then the final state of this whole process is exactly the bit string we want, written in binary. So here we have done just a single query to this oracle instead of n, and we have gotten exactly the output we want. Okay, now for something completely different. Quantum information is a broad field. It has quantum computation as a subfield, but also another subfield is quantum communication. And now we're going to look at a quantum communication protocol in order to get a bit more information about how quantum information differs from classical information and how it allows other things to be possible. And I've already tried this once and I got in a bit of a muddle while trying to draw a circuit at the same time as talking, and that's why there's already a circuit on the screen. So let's look at a case where we need to send 2 bits worth of information and we have classical bits at our disposal. How many classical bits do we need to send 2 classical bits? We need to send 2 classical bits to send 2 classical bits because that's just how bits are defined. How many quantum bits do we need to send in order to send 2 classical bits of information? Well, the answer is also 2, because none of the fancy features of quantum bits allow us to convey more information with them than just a single bit, because if we could, then they wouldn't be quantum bits, they would be quantum something else. However, that doesn't mean that we can't take a fancy approach. So the most obvious approach would be to take our 2-bit string and encode it into qubits and then send those 2 qubits. The person at the end measures them and they get the 2-bit string. But what we can also do is apply the circuit that I've drawn at the bottom of the screen here. So in this first case, applying the Hadamard here will give us a plus state, and then we apply the controlled knot and it creates some entanglement. And what we will get at the end is a state 0, 0 plus 1, 1 with a normalization, of course, but life's too short for normalizations. In the case where we start with 0, 1, we'll get 0, 1 plus 1, 0, with the first term being the one where the controlled knot acts on the 0 part of the superposition induced by the Hadamard, and therefore gives us our original state back. The second one where it acts on the 1 part. Oh, sorry. Oh no, that's right. Yeah. In this case, the fact that we're adding applying a Hadamard to a 1 state means that we get a phase of -1. So we'll get the state 0, 0 minus 1, 1. And in the final case, we get the state 0, 1 minus 1, 0, because again we're applying it to a 1 state and getting that phase of minus. Now we can send this entangled state to our receiver and they get an entangled state, which is more fun than getting an unentangled state, right? So that's cool. Now let's suppose we apply the inverse of this circuit. So instead of applying first the Hadamard, then the controlled knot, we apply the controlled knot and then the Hadamard. And what we will find is that, well, let's just apply the controlled knot first of all. So here we're going to, now I'm going to try and do a circuit while I talk. Here we'll just apply the controlled knot, and what do we get as a result from that? Well, it unpicks this entanglement, so we here would get, well, the control knot does nothing to the 0, 0 state. To the 1, 0, it flips that final 1 into a 0. So we will get a superposition on the first qubit and just a 0 on the second. Then in the next case, 0, 1, it does nothing. 1, 0, it flips a 0 to a 1. So we get a superposition and a 1. In this case, we will get again a superposition, but it will incorporate this phase of minus to make the minus state. And in this case, we get a 0. And in this case, again, we get a minus state, but we get a 1 over here. So then if we were to do the Hadamard, and that was a terrible attempt at doing circuits, it's a Hadamard that messes me up. And it just occurs to me that the Hadamard box is probably partially hidden by the webcam. Hopefully in this and in all cases where the webcam covers up what's going on, it's actually obvious what's going on anyway. And I've spent all of that effort making some space and realised that actually the answer is already there anyway. This Hadamard explicitly takes us to where we need to go. It flips this, this plus into a 0, this plus into that 0, this minus into that 1, this minus into that 1, and this 0 is that 0, this 1 is that 1, this 0 is that 0, this 1 is that 1. It's got a bit binary, hasn't it? So this is another protocol we could use to send 2 bits with 2 qubits, to have the sender encode them in some entangled states and then have the receiver decode them. However, we could actually replace this initial circuit with a circuit that only acts on a single qubit. Before proceeding on to the details of superdense coding, let's take another look at those 4 states. There are actually names for them that are commonly used, which of course have phi's and psi's, because what other things would we call quantum states? So the state phi plus is the one that is correlated in the Z basis and has a plus there. Now this plus also means, and you'll see this if you try rearranging it yourself, that it can also be written as plus 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 minus minus. So it's also correlated in the X basis, and I believe it's anti-correlated in the Y basis. Phi minus is a state which is correlated in the Z basis but anti-correlated in the X basis, which means that we have 0, 0 minus 1, 1. And this can be written as plus minus plus minus plus. And then we have the 2 states psi plus and minus. Let's just save a bit of time by writing them like this. And these are the anti-correlated states for the Z basis. So they are 0, 1, plus or minus, depending on whether you've got the plus or the minus, 1, 0. Okay. Now these can all be obtained from each other by local unitaries, as we call them, which are unitaries that act only on one or the other qubit, and so excluding the non-local unitaries such as the controlled NOT. So the phi plus state can be obtained from the phi plus state by doing nothing. The phi minus state can be obtained from the phi plus state by just flipping the sign from plus to minus on either of these ones, which is done by the Z gate on either qubit. So for example, let's do, well, that qubit. So phi minus state. And the psi plus state can be obtained from the phi plus state by just using an X to flip the correlation to anti-correlation. These are actually all states that you would have seen in Hello Qiskit, although you wouldn't have been given the name of them at the time. And for the phi minus state, you have to do the x to flip it from, for the psi minus state, you have to do the x to flip it from being a phi to a psi, and then a z to flip the phase. So just by applying Pauli's on a single qubit, so let's actually write that out. So psi minus is equal to an x and a z, which means we can write a y multiplied by the phi minus state. Of course, there might be some global phase weirdness there, but who cares about that? So here we see that if we have made a phi plus state, then by applying a z or an x or a y, or in this case nothing, we can rotate it to any of these four orthogonal maximally entangled states that we call the Bell basis. Now this is quite interesting for this protocol because it means that the way that Alice, so I haven't brought up the names Alice and Bob so far, but in these quantum communication protocols, when we have someone who is sending a message to someone else, they're usually called Alice and Bob. So when we have this case that Alice wants to send a bit string of 2 bits, B1 and B0, she could do that process as before by turning 0, 0 into, so encoding 0, 0 as the state phi plus, and so on and so forth, and sending them to Bob. And she could do that by encoding the bits in a 2-qubit state, and then applying the circuit that we considered and getting the Bell state, sending it to Bob, and he decodes it. However, there is another way, which is that irrespective of what message is being sent, Alice could first create the phi plus state, and then in the case that she wants to send 0, 0, she would do nothing. If she wants to send the 0, 1 state, then she would prepare the phi plus state by applying an x to her qubit. I mean, to one of the qubits. Spoilers. If she wanted to prepare the 1, 0 state, then she would apply a z to one of the qubits. And if she wanted to apply, so if she wanted to send a 1, 1 state, so then she would apply a y to one of the qubits. And then she can send to Bob. Bob can decode in exactly the same way as before. Now what is interesting here is that the only thing that Alice needs to do after she already knows what message she wants to send is apply a Pauli to one of the qubits. So that Pauli is one of the 4 possible Paulis, identity X, Y, or Z, depending on which one of the 4 possible states that she wants to send. So what she can actually do is prepare this 2-qubit state, send one of the qubits to Bob before she even knows what message she wants to send. And then, once she knows her 2-qubit message she wants to send, she applies a Pauli to the qubit that remains, which is why I called it her qubit earlier. And then, after having done that, and knowing that the 2-qubit state is now in the required Bell state, she sends the other qubit to Bob. So what's interesting about this is that after having learned what the message is, she only has to send one qubit to Bob in order for him to work out what the message is. So it's, in some sense, almost as if she's only sent one qubit and nevertheless sent 2 bits with it. It's not really true because she has actually sent 2 qubits. She just sent one of them beforehand. Although you could also have a situation where some middle person, who's neither Alice nor Bob, creates a entangled pair, a pair in this phi+ state, sends one of the qubits to Alice, sends the other one to Bob. Alice then applies the Pauli she needs to apply in order to send her message and sends her one onto Bob. And now, really, Alice has only sent one qubit to Bob and yet sent 2 bits of information with that, exploiting an existing resource, which was an entangled state. So it doesn't break the fact that you can only store one bit in one qubit, but it does add a bit of extra quantum flavor to that statement. You can also use entanglement as a resource to do kind of crazy stuff. And another example of that is teleportation, which unfortunately is not the same kind of teleportation that we find in Star Trek, but it's also pretty cool. And also, what is the teleportation that we find in Star Trek? You know, there's philosophical ideas of identity that can be talked about here. Anyway, let's not get too much into that. The Bell basis is a basis, so it is a set of 4 orthonormal states that completely span the state of 2 qubits. Any state of 2 qubits can be written as a superposition of the Bell basis states, and we can imagine a measurement which measures which of the Bell basis states that we are in. And just the same way as the X basis measurement can be done by doing a Hadamard and then a Z basis measurement, a bit of a hack to make it possible for us to do something that has the same effect. Similarly, a Bell state measurement can be done with the Z basis measurement, and that's exactly what Bob did in the last protocol by sort of disentangling it and turning it into Z basis states. If after the measurement he re-entangled it, it would be back to the Bell basis. Anyway, so it's a basis, we can measure in it. The fact that it's entangled does not stop us doing that. And any 2 qubit states can be expressed in this basis. And that's what we're going to do now while looking at teleportation. So we are going to start off with an arbitrary state, and of course with arbitrary states we usually call them psi, because we call everything psi, but there's already psi's on the board, so let's call it something else. Let's call it Sigma in honor of Star Trek, because, you know, this is teleportation. So Sigma is a quantum state we don't know. If we did know it, then this would be a very different protocol. We would be talking about fax machines, essentially, because we're really talking about a protocol where Alice has a quantum state. She wants Bob to have that quantum state and for her not to have it. So if she knew what the quantum state was, she could just tell Bob, hey, it's this particular superposition. You know, you just have to do an RX and a CX and a whatever to get it. And he would make it, and Bob would throw her qubit in the bin, or measure it and reset it to 0. But if it's an unknown state, then she can't do that because she doesn't know what it is. So is there some way that nevertheless she can make it so Bob has it? Well, one way is to, send it in the post, but that's boring. Let's see if we can find a way where no quantum stuff has to be transferred from Alice to Bob, and yet somehow the unknown quantum state is sent in some sense. So what we are going to do is start off with a state where we have our unknown quantum state, but also a pair of qubits in the state phi+. And here the unknown quantum state is going to be in the possession of Alice. And one half of this entangled pair is going to be in the possession of Alice. And the other half of this entangled pair is going to be in the possession of Bob. Now, how was this done? Maybe they had previously done something to share this entanglement. Maybe they'd gone to a conference and the swag at that conference was to give out different halves of entangled pairs. However it happened, and that's a resource that we can exploit in this protocol. Okay, now what we are going to do, to take a very broad overview, of the protocol is Alice is going to measure in the bell basis, and so she is going to force these two qubits to become phi plus, phi minus, psi plus, or psi minus, because that's the only choice they have. When you measure in a basis, it is forced to become one of those basis states. And now let's suppose that the result she gets is phi minus, then what will be the resulting state of Bob's qubit? It used to be half of an entangled pair, but the other half of that entangled pair is now gone off to have its own life. So what's going to happen to Bob's qubit? Well, by symmetry, you can think, well, maybe it's psi. Maybe this unknown quantum state has somehow popped out on Bob's side because it has nowhere else to be. And, well, it is. So that's good. But A, how do we prove this? And B, what happens if Alice gets other results? And, well, we just need some maths. That's all we need. So let's take our unknown state again. That is a terrible attempt at a sigma. Maybe I should take the lesson that the Bluetooth doesn't like sigmas and go back to nice psis and phis. So yeah, we've got this particular state. And now let's write this out a little bit bigger. So the psi state can be written as some superposition where we have some, well, let's call it S0. Actually, let's not call it S0. We've had S0s meaning completely different things in the earlier parts of this lecture. So let's go back to just calling the coefficients C0 and C1. And this is tensor producted with the phi plus state, which is 1 over root 2, 0, 0, plus 1, 1. So if we expand out these brackets, if we use the tensor product to make them into just single 3 qubit states, then we have 4 terms, C0 times 0, 0, 0. So that's for when we multiply this term by that term. And of course we have to close the bracket as well. Oh, actually, there's also going to be the good old 1 over root 2, which we should never forget about. So let's sneak that in over here. And then we have C0 times 0, 1, 1, which is this same term, but with this one. And then we also have C1 times 1, 0, 0, and C1 times 1, 1, 1. Yes. Okay, so if we now collect terms and try to rearrange this so that it's now the first 2 qubits expressed in the bell basis, then we can see that this term and this term over here are going to be involved with the phi parts because they're correlated. This term and this term over here are going to be involved with the psi parts because they're anti-correlated. So explicitly the 0, 0, 0 term is going to turn into the superposition of phi plus and phi minus tensor producted with 0. And similarly, the 0, 0, 1 is going to be phi plus plus phi minus tensor producted with 1. And the 0, 1, 1 and the 1, 0, 0 are going to be similarly expressed, but with the psi plus and psi minus cases. And once we do this, we find that we can express sigma tensor phi plus as, hang on, I missed one, didn't I? There should also be a 1 over root 2 there. So sigma tensor phi plus can be expressed as a superposition with phi plus tensor sigma as one of the terms. And the reason for this is because when we look at this term with the 0, 0, 0, then the final 0 here, the final one. Okay, now I've managed to sort of scroll on it enough. That final 0, 0 is going to become associated with this coefficient C0, whereas in the other term, which has one of these phi pluses, then the final 1 will be associated with this coefficient C1, and therefore they will combine when we collect terms to give us a sigma, because what is sigma but C0 times 0 and C1 times 1. And then we'll also have a bunch of other terms for what happens when you get the other basis states. And basically what you find is the other basis states will give you in this part either x times sigma or y times sigma or z times sigma. So what happens is then that Alice makes a measurement. She gets one of 4 possible results, either phi plus, psi plus, phi minus, or psi minus. If she gets phi plus, the same state she started out with, then the state that pops up over Bob's side is sigma, the state she wants to send. Otherwise, it is either x sigma, y sigma, or z sigma. So if Bob looks at his qubit without knowing what is going on there, it's either going to randomly be x sigma, y sigma, or z sigma, and he doesn't know which. And because of that, it just looks like a completely random state. He cannot deduce any information about whether Alice has done anything, and if Alice has done something, what the results were. So he can't tell what the results from her measurement would be. Quantum mechanics very nicely is obeying the rules of special relativity and not allowing information to be transferred faster than light here. However, all Alice has to do is to get on the telephone with Bob and tell her, hey, I got a phi minus. And then he immediately knows that what he has is the state sigma, but rotated by some Pauli. He can apply the same Pauli to undo it, and we have this process of teleportation complete. So if Alice does a measurement and forces the 2 qubits on her side into the state of the original entangled pair, then by symmetry Bob just gets the state that she wanted to teleport, and otherwise she just has to transfer some classical information, some bits, and he is able to receive a quantum bit, an arbitrary state of a quantum bit. So there is a way to send an arbitrary quantum bit using 2 classical bits, which is the amount that she needs to send in order to convey this information, as well as a pre-existing entangled resource. But no actual piece of quantum hardware has to be sent. And that's pretty cool. And that is quantum teleportation. So in this lecture, we have gone through Bernstein, Vazirani, and Deutsch-Joseph, and also Superdense coding and teleportation. And these give us immediately some idea of what can be done with quantum information and how it can be processed, but also some perspectives from quantum communication theory. So I hope these motivate you to see that quantum computing is something that can do things that we cannot do without qubits, and now we can go on to the more useful textbook algorithms, the ones on search and factoring that we expect that people will actually want to run when we get the hardware. But that is all for this time. Thank you for listening.